So if ever the connection get lost, please stay connected or connect again, and we will try to solve any issue concerning the internet connections. So Philip, I think we can start. I let you introduce yourself and go ahead with your presentation. So, thank you.
All right. Okay. First of all, thank you, Yassine, for the invitation and the introduction, and thanks for Magnetic Society for arranging this online seminar series. First of all, I'm Philip Pong from the EC department in New Jersey Institute of Technology. So today I will talk about the contactless sensing in condition monitoring and anomaly detection for smart grid. New possibilities and alternatives. I will talk for about 15 minutes, and then we will have about 10 minutes for Q&A. And because of the limitation of time, I will try to be brief and concise. And I also write down the papers that we publish, and the details can be found there. And of course, I will also be happy to discuss with you all offline. And also, I would like to say that, okay, this work is the teamwork for the past 10 years, okay, my students and my postdocs and collaborators. So I would like to give credit to them. So before the starting, I would like to give a little bit of background of myself, because what I'm doing and what I have been doing has a lot to do with my background. So I was born and raised in British Hong Kong, and I did my degree in electrical and electronic engineering. And so my background is an electrical engineer. And then I did my PhD in the United Kingdom, and there I did instrumentation. I do the scanning tunnel microscope, which is a high precision instrument that can be used to observe atomic structures. So it requires high precision and suppression of noise. And that led me into the postdoc work, where I did the ultra sensitive sensor fabrication in the National Institute of Technologies and National Institute of Technology and Standards Technology in Maryland, in the United States, where I fabricated magnetic sensors. And after I moved back to Hong Kong in 2008, I started to work on the application of sensors in smart grid and smart city, and have conducted a few power industry projects. And then in 2021, I started my position in New Jersey Institute of Technology. So currently, my research interests include making the sensors hardware, doing the sensor fusion, do the data analytics with machine learning, and have developed the systems, the sensor system for condition monitoring in smart grid and smart city. So today is a talk for Magnetic Society, and so I talk a little bit on magnetics as well. So why are we interested in magnetic sensing? Okay, for example, for magnetoresistive sensors, okay, MO sensors, okay, for TMO sensor, okay. So the sensor work like this, okay. Its resistance changes in response to the external magnetic field. Okay, the sensors are pretty small. Okay, some commercial TMR sensor is just a couple of millimeters across, and some groups and companies say, okay, they have a sensitivity close to or down to 1 picotesla. And so, what is the idea of 1 picotesla? So the Earth's magnetic field is about 10 to the -5 Tesla, and the magnetic field from the overhead lines at the ground level is about 10 to -6 Tesla. So you can see there's a lot of room for detection. Okay, the sensitivity of the sensors nowadays for MO sensors, which is so small and compact, can have a sensitivity several orders of magnitude further sensitive than the signal. Okay, so it has a lot. It opens up a lot of possibilities and alternatives for sensing, and particularly contactless sensing. So smart grid, okay, cover generation, transmission, distribution to consumption. So for our team's work, we have been trying to develop contactless sensing for transmission and distribution, and then for renewable energy and wireless power transfer. So today, I thought we'd talk on these 3 aspects. So why contactless sensing? Okay, so first of all, okay, so we know that condition monitoring is very important. Okay, it indicates the current condition, suggest maintenance, minimize downtime. However, it requires sensors, as we will talk about later on. So why do people not deploy sensor? Because cost is important. Okay, people are waiving between the benefits of sensor and cost. Okay, and cost include installation cost, maintenance cost, footprints, and safety. Okay, so contactless sensing can make the installation much easier and much safer. And therefore, and also it allows the retrofitting to the existing equipment or plants. So which is critical for scalability. Okay, because if it cannot be retrofit to the existing plants, then there is a limitation to the deployment of sensors. And the workflow is like this, okay, for condition monitoring. Okay, first of all, you acquire data with sensors, and then you pre-process it, and then you identify condition indicators, train the model, deploy, and integrate. And the whole thing starts with sensor, acquiring the data, okay? And then with this data, then we do some pre-processing, okay, like using the wavelet analysis, PCA, to remove the noise, and then convert the data to frequency domain, etc. So these days, people talk about condition indicators for machine learning, okay? So you can use signal-based condition indicators or model-based condition indicators. And for signal-based indicator, we can have the time domain data, frequency domain data, or so-called time frequency domain data, which is popular for convolutionary neural network. And for time domain, for example, you can extract the mean, standard deviation, and for frequency domain, as we know, okay, from the PPT, from the FFT, you get the mean frequency, peak frequency, etc. And time frequency domain, you can look at the spectrum entropy, spectrum kurtosis, etc. So that you can develop various kinds of condition indicators that indicates the anomaly or fault. Okay, so people have been doing that, and for the data that you get from magnetic field, you can do something similar. And the good things about condition monitoring is you can do the detect the anomalies, as I mentioned, and you can classify faults. Okay, you can classify what is the problem. Okay, what kind of fault it is, and then you can also predict what is the remaining useful life. Okay, so that we can do the maintenance just in time and avoid the catastrophe of breaking down. So talking about contact sensing, okay, so today we talk about smart grid, right? So power grid, so two things, okay, current and voltage. So how can we do the contact sensing? Now for traditionally for current sensing, okay, you can use the Ohm's law, you can use the magnetic field sensing, you can use the Faraday effect, you can use the Faraday's law of induction, okay? So for contact sensing, you can use the Faraday effect, which is an optical effect, or the magnetic field sensing, okay? So for my team, we work on magnetic field sensing because, as I mentioned, the magnetic sensors are very small and it's very cheap and its sensitivity is very good. Okay, whereas for Faraday effect, okay, you need to use some optical means. Okay, that means you need to use some optical sensors. Okay, which is typically more complicated and more expensive than solid-state magnetic field sensors. Similarly, for voltage, okay, so for voltage, you can do the sensing by Ohm's law, Faraday's law of induction, electric field sensing, Pockels effect. So Pockels effect is the optical effect, and the electric field sensing, okay, you can do the contactless sensing by electric field sensing, similar to the case in current. Okay, so I will talk about that later on. So what it means is by electromagnetic field sensing, you can do contactless sensing for current and voltage in the power grid. So we know that, okay, sensing is important. So why magnetic sensing? Okay, so we all know that for magnet, it has magnetic dipole moment. And if you have the magnetic dipole moment, you have the magnetic field lines, and then our magnetic sensor can sense the magnetic fields. And the concept of magnetic dipole, okay, is not restricted to modeling of atomic size particles. Okay, so in magnetic society, okay, a lot of colleagues work on micromagnetic simulations, okay, which is at the micro scale or nano scales, okay, but actually in macro scale, okay, things can also briefly possibly treated as a dipole and then we treat it like a giant magnet like that, okay. So a compass, MR scanner, or even the Earth itself is essentially a dipole, and with the magnetic field sensor, you can sense the magnetic field emanating from the magnet. And also the as we know from the fundamental cause of electricity and magnetism, okay, we know that, okay, the Biot-Savart law relates the relationship between magnetic field and the current at certain position in space. So by measuring the magnetic field, we can work reversely to find out the information of the current conductor, including the current that it carries as well as its position. And you can do it contactlessly. Okay, that means you can do it at a certain distance. Okay. And even for a two-wire cable, okay, one in, one out. So if you put the MR sensors on the cable surface, you can still resolve the current for the in and out current. And this is suitable for large-scale application because contactless sensing is low cost and easy installation. Okay, and that will enable pervasive sensing, which we will talk about later on. And another reason why we do magnetic sensing is, as we know, okay, for sensor, okay, so what we do is essentially we convert the measurement to an electrical output. Okay, so in this universe, pretty much we have 6 forms of energy forms that the measurement can take. So measurement is a physical quantity or property or condition which is being measured. So in this universe, typically there are 6 energy forms, okay, mechanical, okay, such as length, area, volume, thermal, okay, temperature, specific heat, electrical, okay, voltage, current, magnetic, field and flux and magnetic, and then radiant, okay, polarization, chemical, pH, reaction rate, etc. So magnetic is one of the 6 major energy forms that measurements can take place. So it is one of the forms that the signal that typically exist. And our modern civilization relies on electricity, and magnetism exists everywhere in our everyday life, okay, in the overhead lines, underground cables, and the motors, generators, and in wireless power transfer. So these days so magnetic field is everywhere. So therefore, magnetic sensing is very important. So I talk about why do we need sensors and why do we do contactless sensing and why do we work on magnetic sensing. So now let's take a look at how contactless sensing can contribute in transmission and distribution. So 3 major choices for the existing power grid. So number 1, okay. So nowadays we talk about we talk a lot about renewable energy. Okay, because the new transmission lines are very expensive to build, and also time consuming. Okay, and also a lot of people object to the building of new transmission lines. So it's very hard to build new lines. So a lot of time we need to make do with our existing transmission lines, and that often lead to overloading, and that can lead to heating and then the sagging. So the sagging needs to be monitored. Okay, so we need some means to do the cable spatial position measurement. Okay, so as to enable so-called a dynamic line rating. Okay, so that we can overload the cables temporarily to accommodate the additional renewable energy sources. And even though the power grid is over 100 years old, but still a big chunk of the areas of the power system is not monitored. So we don't have enough sensors and sensing capabilities. Especially now the grid is getting more and more complicated. Okay, so traditionally we have the SCADA, but they typically only at the substations. Okay, when you are in the open wire, okay, you don't have the sensors. Okay, so those are CTPTs. They typically only exist in the substations. Okay, so a lot of time, okay, so where is the fault? What is the fault? And a lot of time they need to actually send engineers or workers to walk along the line to see what is happening. Okay, for example, in the United States, okay, so on average, okay, you only got one substation every 60 kilometers of transmission line. So you can see, okay, it's just a ballpark estimation, but it can say it can tell us that, okay, there's not much sensing and visibility in between. So another thing is expansion. Okay, the penetration of renewable energy, which is highly variable and uncertain. And as we know, in the power system, the supply demand has to be matched. Okay, if there is a mismatch in supply and demand, then it will affect in the system frequency and phase angle, and that led to the power system instability. Okay, so therefore we need to have some sensing technology that can help us to monitor the power system stability, including to looking at the frequency and the phase angle. So how do we monitor the current, for example, in the transmission or distribution lines? Okay, so for one 3-phase circuit, okay, 3 conductors, 3 phases, and then sometimes you have more than one circuit. Okay, maybe you have double circuit, then you have more than 3 conductors. Okay, and also there are abnormal situations in spatial and electrical aspects. Okay, for example, the sagging and the galloping. Galloping means the swinging. of the cables, overhead cables, and then there can be imbalances in the current amplitudes and phase. So all these need to be observed, and it can be difficult to solve this multivariable inverse problem analytically. So we have developed the iterative technique that can solve this problem iteratively. Okay, so basically we use an array of ML sensors to do a series of measurement, and then from the series of measurement we can put into the iterative algorithm to solve for the current as well as the position of the conductors. So first of all, okay, let's take a look at those computational calculation. Okay, so let's imagine, okay, we have a 500 kV transmission overhead transmission lines. Okay, so if we have a configuration like that at the ground level, okay, so as you can see, the magnetic field measured at the ground level varies with the sagging. As you can see, as the cable sag, the magnetic field distribution varies. Okay, and then also for galloping, as you can see, as the galloping varies, okay, the magnetic field varies with the galloping. Okay, and then for current imbalance, you can also see. Okay, so with the magnetic field vary with various degree of current imbalances. So which means that by measuring the magnetic field at the ground level, you can obtain information about the cable position as well as the electrical information of the overhead lines. So we go one step ahead and makes things more complicated. For example, okay, so let's do a double circuit. Okay, you have the ABC circuit 1 and ABC circuit 2. And again, by doing the computation, we find that the magnetic field on the ground level can reflect what is happening up there in terms of cable positions as well as electrical information. So therefore, then we try to get the magnetic field at the ground level and then input to the iterative technique that we developed. And then we solve for the cable position as well as the current information. So as you can see here, okay, so even when there's a sagging of 10 meters, and even in the case with sagging as well as galloping, we can still reconstruct the cable position accurately. And in the case when there is current imbalance, for example, in phase B, there's a 10% current imbalance, we can still reconstruct the cable position as well as reconstruct the phase currents curve accurately. And in terms of so here we have the imbalance in current, and then here we have the imbalance in phase. Okay, we can still reconstruct accurately with very small error in the spatial parameters and electrical parameters. So so the system frequency, we can also extract the system frequency from the phase curve that we reconstructed. So that means this in response to the power system stability measurement, okay, we can measure the frequency as well as the phase angle accurately. Okay, so this is useful for power system instability or fault conditions monitoring. Okay, so and then some people say, hey, measuring the magnetic field on the ground level can be problematic. So what if the landscape does not allow you to have the magnetic measurement on the ground level? For example, there's a river. Okay, so then we try to put it on the tower top. Okay, and so in the simulation we have the we put the sensor at the tower top, and we find that okay, the reconstruction can still work the same accurately. And we also go on to build a lab test bed. Okay, we in the lab we have a scaled test bed to do the experiment, and we find that okay, we can also solve the problem equally well if we put the sensors above the transmission lines. And earlier on, I mentioned that okay, we can also measure voltage contactlessly. Okay, so here, so basically we try to make use of a electric field sensing assisted with the magnetic sensing. Okay, the magnetic sensors help us to determine the position of the cable, and then we use the electric field sensing to measure the voltage of the overhead lines. So the idea is the overhead transmission lines induce voltage in those induction bars at the ground level. Okay, because there is essentially there is a capacitive coupling between the overhead lines and the induction bar. So which can be represented by this electrical circuit. Okay, equivalently, you can describe the relationship between the overhead line voltage and the inducer voltage by this matrix equation. So by this component voltage transformation matrix, we can correlate them together, and then you can reverse it to find the voltage of the overhead lines. So here is the test bed that we built in the lab to verify the technique. And we can also deploy a technique for underground cables. Okay, underground cables are typically like this. Okay, 3-phase 3-core cable with the insulation outside, and then we put the sensor on the cable surface, and then we run the iterative technique that we have developed. And then as you can see, again we can reconstruct the cable position as well as the current curve accurately. Okay. So here is the so we did the experiment on a 11 kV cable that we take from the power companies. As you see in the experiment, okay, it can work in the experiment. And also we have done the on-site application. Okay, so we go beyond the laboratory and go to the actual substation to deploy the technology. Okay, so in the actual environment, okay, the situation is more complicated because you have the noise from the surrounding, okay, you have other laboring cables, and you have background noise, etc. So as you see here, okay, we have a triple layer shielding to reduce the effect of external interferences, and also we have the magnetic flux concentrator to concentrate the signal for the sensor. Okay, now here we over-engineer a little bit, okay, because at the time we just want to do the proof of principle. Okay, so we over-engineer a little bit. So triple layer may be a bit too much. Okay, so even one layer we believe it will be okay, and even without it may be okay. Okay, so but here we try to make sure that it will be all right. So then we build a platform in the lab, and then we bring the platform to the site. Okay, here's a substation in Hong Kong. So my student and I work together to install the platform on the cables there. So as you can see here, outside the shielding, there is a background magnetic field of 0.6 microtesla. And once inside the shielding, there's a low detectable background magnetic field. So the shielding is very effective. Okay, so and then we do the measurement with our setup, and then we compare with the readings of the instrument in the substation, and we find that our measurement is very close to or identical to what the instrument measured there. So that verifies that our technique is correct, and the error is less than 5.5%, and we can still further improve the accuracy. Okay. And moreover, so I want to briefly talk about this. A lot of time, okay, so sometimes people, the workers, they do the excavation work at the ground, and then they accidentally dig into the cable, and that causes the explosion, and that can be dangerous. And that is because we currently do not have technology to detect voltage energized cable. Okay, so we have technology to detect current energized cable, but we don't have technology to detect voltage energized cable. So what is voltage energized cable? So the voltage energized cable has voltage but have low current. Okay, so traditional cable avoidancy tool cannot detect them. But for our new technique, we can distinguish all three status accurately, and that can help to help the workers or engineer to identify the energization status of the cable before doing excavation work. So to summarize, okay, our technique, the main advantage of our technique compared to the traditional means of CT, current capture, or Rogowski coil is it is contactless, okay, and it can do the multi-phase, multi-core detection at the same time. Okay, so for the others technique, they can only measure the current individually for each conductor. Okay, for us, we can measure all the conductors at the same time. The bandwidth is high, it can go from DC to megahertz. Okay, so which is very important for obtaining the signal for the transient, which is so important for fault identification. So just want to say that, okay, all this technique I mentioned about has been done in proof of concept, testbed validation, and a lot of them has been done by on-site experiment, and they have been done by my group and also by other groups. So this is not some far-fetched dream. Okay, this is something that is already practical and feasible and waiting for us to use in the actual environment. So next topic is the renewable energy. So so contactless sensing with magnetic sensors, okay, can also be useful for renewable energy. For example, for the photovoltaic system. Okay, so PV system. Okay, a lot of time you need to have the power electronics. For example, to do the DC-DC conversion. And in DC-DC conversion, a lot of time you need to have the aluminum electrolytic capacitors for filtering the input and output voltages. And a lot of time, the failure of the converter is due to the failure of these capacitors. And we know that by we can monitor the health of the AEC by looking at the equivalent series resistance and the capacitance. Okay, so by measuring the ESR and the capacitance, we can see if the AEC is going to wear out. Okay, and we found that we can make use of MR sensors to measure the ESR and the C, and in this way we can monitor the health of the AEC. So here we built the laboratory test bed, and as you can see here, the ESR and the capacitance that we found by the MR sensors is very close to the values that is measured by the other instrument. The error is rather small, and then in addition to the determining the ESR and the capacity of the AEC to monitor its condition, we can also do the arc fault detection in the PV system. Okay, because a PV system is a DC system, so DC arc detection is very important for the PV system to operate reliably and safely. And we find that by TMR sensors, we can detect the DC arcing. So how do we do that? Okay, if you look onto the right-hand side here, okay, so from the noise spectrum, you can see, okay, there's a distinction between sustained arc, normal operation and sustained arcing. So essentially, you can see that the 1/F noise, or so-called the pink noise, is much larger when there is a DC arcing occurring. Okay, so and then we try to deduce some parameters from the noise spectrum. For example, okay, so I don't have time to cover all the details. So if you're interested, you can look into our paper here. So basically, we have a parameter P, which is derived from the spectrum. And as you can see, the parameters P can clearly distinguish the situation between normal operation, which is down here, and sustained arcing, which is up here. Okay, so with the magnetic field sensing, and the noise spectrum analysis and the determination of the parameter P, we can distinguish if there is an arcing occurring in the DC system. And we built a small off-grid on the rooftop. This is a rooftop of a building. It's an off-grid test bed. It's a small microgrid here, and we do the testing there. And we find that, okay, in this actual application, we can still use this technique to determine there's a arcing or not. Okay. Now, beyond the PV system, we can also use the contactless sensing in motor or generators. Okay, so here we find that, okay, we can use MR sensor for velocity measurement. Okay, so traditional people use the optical encoder to measure the speed of the motors or generators. Okay, and here we find that, okay, by deploying the MR sensors outside the motor or generator, we can also determine its velocity. Okay, so first of all, we carry out the magnetic equivalent circuit model for theoretical analysis, and then we do the FEM simulation to look at the magnetic field distribution outside the cable surface. Okay, and we find that, okay, there's a we can observe the revolution of the motor or generators from the magnetic field pattern. Okay, but of course you have to put the magnetic sensor close to the motor. Okay, you don't need to put it inside. Okay, put it onto the surface. Okay, but close to the surface, because as we all know, the magnetic flux, it drops due to the inverse square law. So you want to put it close to the motors or generators. And then we find that the stray in the tangential and the radial directions, okay, the pattern is rather clear, okay. You can also still see in the axial direction, okay, but much weaker, okay. So as you see here, okay, we can see the pattern that from the pattern you can divide, okay, this is one revolution, and then from the period of time that you can determine is a velocity, okay. And also here you can see even in a dynamic situation where the velocity is varying. Okay, you can see the velocity is varying. Okay, the speed is varying, and we can still determine its velocity accurately with this technique. This is the test bed that we have in the laboratory. Okay, so this technique is not just verified by simulation, but it is also verified by experiment with a test bed in the laboratory. And then we find that our sensing technique can also be useful in detecting the interterm short circuit fault for permanent magnet synchronous machines. Okay, and as we know, permanent magnet synchronous machine are very common in wind turbine. Okay, so in the term short circuit, sometimes inside the term you have short circuit, which you cannot see from outside. So we find that okay, we can detect this kind of fault by having the magnetic sensor outside. Okay. So because it's a straight magnetic field provides information about the phase currents as well as the status of the stator windings. Okay, and we can also detect the location as to where the short circuit is by looking at the magnetic flux. Okay, so again we look at the magnetic equivalent circuit, and also we do the FEM simulation. And then from the FEM simulation we can see that the magnetic flux in the radial direction and in the tangential direction, it changes correspond to the occurrence of the short circuit fault. And then we go ahead to build a test bed. Here is the test bed in our laboratory. So we put the sensor, okay, for example, TMR 2503, TMR 2001 outside to do the sensing outside. And we have a 24 TMR sensor array to measure the stray magnetic field outside the permanent synchronous machine. And then and we have also developed a fault location algorithm, which is based on the magnetic flux density ratio to locate the short circuit fault. Okay, and with this technique, both the location and the severity of the fault can be determined. Okay, so as you can see, okay, in this directional diagram, you can see this indicate okay where the short circuit is, and also the ratio here indicates the severity of the short circuit fault. Okay, and then another fault that we can detect in the permanent magnet synchronous machine is the magnet defect. Okay, now sometimes the magnet doesn't work. The magnet does not work forever. Sometimes they got broken. Sometimes they lose its magnetism, etc. And and we need to detect this kind of problem so that we see that okay, maybe the machine is going to fail. Okay, so that we can do the maintenance or replacement. Okay, so the flux leakage contains information about the health condition of the inside magnet during the machine operation. Okay, it is measured by magnetic sensors outside the permanent magnet synchronous generator. So so first of all, okay, we build the FEM. Of course, we do the equivalent circuit analysis, okay, magnetic circuit analysis, and then we do the FEM simulation in JMAC. Also, as you can see here, when it is in normal situation, the amplitude of the B magnetic flux leakage is constant, and you don't have a DC component. The DC component is more than 0. And when there is a defective permanent magnet, then the amplitudes of the magnetic flux leakage as well as the DC components varies during the operation. Okay, you can start to see some variation, some patterns there. And then in addition to the simulation, okay, we also build a test bed. So as you can see here, okay, we deliberately break the magnet in the machine, and then this is our test bed in the lab, and here is the TMR sensor outside the machine. And the TMR sensors are pretty small. Okay, they're just a few millimeters across. Okay, they can be put onto the outside of the machine. And the as you can see, okay, from the envelope of the leakage magnetic flux and the DC component, you can see during normal situation and during the defective when there is a defective magnet, the situation is very different, and that can be used to distinguish between the two situations. And also from the spectrum, you can see when there is defective magnet, okay, there is more peaks towards the lower harmonic orders, okay. And another fault that we can detect with from the magnetic flux measurement is the so-called eccentricity fault. So eccentricity fault is basically what it means is that the rotor and the stator, their center do not align with each other, okay, which can be caused by manufacturing imperfection and mechanical deformation during the operation. And eccentricity fault is very common fault in generators. It can reduce the generator's service life and even lead to the system breakdown. So it is important to detect this kind of fault. And there are two types of eccentricity fault, including the static eccentricity and the dynamic eccentricities, and there's a mixed eccentricity. And the effect of the different eccentricity faults can be, first of all, we analyze by the magnetic equivalent circuit, then we go on to do the FEM simulation. And then as you see, okay, when there is eccentricity, you can see there's a difference in the magnetic flux leakage pattern. And then based on the magnetic field data, okay, as I mentioned earlier on at this talk, okay, we can try to develop some condition indicators from the sensor data. Okay, so here we develop an indicator for the static eccentricity. We also develop an indicator for the dynamic eccentricity based on the magnetic field measurement. Okay, so I don't go into the details. For colleagues who are interested, you may refer to our papers here. So by deducing these two condition indicators from the sensor data, we can use it to distinguish between normal situation and situation where you have the static eccentricity problem, and also distinguish the situation where the situation is normal and the situation where you have the dynamic eccentricity. And this algorithm is very the computational burden is light, so which leads to a fast detection test speed. And here is the test bed. Okay, we build a test bed and do the experiment, and as you can see, okay, the amplitude as well as the direction of the eccentricity fault can be indicated from the condition indicators. So so the experimental result validate our technique. All right, so I finished talking about the contribution of contact sensing to the distribution and transmission and to the renewable energy. Now let's talk about the last topic, which is the wireless power transfer. So these days we talk about electric vehicles. Okay, so one problem of electric vehicle is its range. Okay, so one charging it can go about 400 miles, 300, 400 miles, approximately that range. Okay, and then you need to recharge. Okay, so how do we extend the range of EV is important. So some people propose, okay, hey, can we do the dynamic wireless charging? Okay, that means we install the transmitting coil underground, for example, on some highway. Okay, so that we can continuously charge our electric vehicles. Okay, so with the receiving coil on the other side of the vehicles, the vehicle can receive the energy by magnetic resonance coupling. Okay, and in order for this to work, we need to detect the misalignment, because the power transfer efficiency depends on the misalignment between the two coils. Okay, so so here is the test bed that we built in the lab. Okay, you can see our TMR sensor array here. Okay, and we also have the current probe. So here is the TMR201 sensor array. And first of all, we calibrate is a sensing curve. And then as you can see here, when there's under various situation of the misalignment, okay, the receiving current, okay, the IR varies. Okay, when there's no misalignment, the IR is the largest, and when it's misalignment, the IR decreases. Okay, which means the receiving power is decreasing when there's misalignment. And we can determine the misalignment situation from the magnetic flux measurement by the T-mount sensor array as shown here. Okay. So, and then we go one step forward. In addition to having a array, we build a sensing matrix with TMR sensor. Okay, so the TMR sensor array not only measure the magnetic flux, but it also can be used to determine the mutual inductance. The mutual inductance is proportional to the transferred power, and therefore we can determine the transferred power from the measurement of this sensor matrix. And also we can determine the metallic object in between the receiving and transmission coil. Okay, we don't like foreign metallic object because a foreign metallic object can greatly disrupt the power transfer. Okay, and we can also from the matrix measurement, we can also determine the symmetric coefficients Cx and Cy, so as to see, okay, how do they how is the misalignment situated? Is it tilted this way or tilted that way? Okay. So here is the test bed that we the matrix test bed we built in the lab, and we use the Helmholtz coil to calibrate our sensor for the three-dimensional sensing. The simulation show that, okay, as there's a misalignment, the receiving power has decreased, and then as shown here in this experimental measurement, we can see that the misalignment measured by our sensor matrix is very similar to what we found is very similar to the simulation results, and also the measured power and the measured mutual inductance is very similar to measured by the LCR meter or measured by the current probe. Okay, that means our calculation from the magnetic flux measured matches with the instrument measurement. Okay, here you can also see that the Cx coefficient can also be accurately determined. Okay, so we have also tried to put a metallic object, for example, put a metallic screw in between the transmission and distribution coil, and we can see that, okay, the metallic object can be accurately distinguished, okay, by the field or large field offsets. Okay, and then we go one step further to try to do some control strategy. Okay, so if we can detect the misalignment, okay, so here instead of having one coil, we have three small coils: coil 1, coil 2, coil 3. So depending on the misalignment of the between the receiving and transmission coil, the algorithm select using coil 1, coil 2, or coil 3 to receive the power. Okay, and as you can see by the transitional structure, the efficiency is like this. But by using this strategy, okay, the efficiency is like this. Okay, in worst case scenario, it can improve the efficiency from around 14% to 76%. Okay, so that goes towards the end of this talk. So we have talked about the contribution of the contactless sensing in transmission distribution and in renewable energy and in wireless power transfer. So as you can see, it opened up a lot of new possibilities and alternatives for smart grid. Okay, so therefore it can bring us into a new era of a new age of a so-called cyber-enabled grid. Okay, because of the contactless sensing, as I mentioned, can facilitate, enable the pervasive sensing, okay, for the grid from generation, transmission, distribution to the consumer side. Okay, as shown in this illustrative diagram, okay, so that we can deploy sensor all the way from generation, okay, from the renewable energy farm to the transmission, distribution, and to the user at the microgrid, etc. So which can be used for microgrid control and energy management, power quality monitoring, topology estimation, and also how we can use the data to determine the price for the energy market. And then for the substation, okay, as I showed you earlier on, okay, it is already practical and feasible to do those all these contact sensing in the substation. Okay, so we can deploy the contact sensing from transmission lines to the distribution lines, for the underground cables, transformers, circuit breakers, and various meters and protective relays to facilitate the smart grid. There is already commercial products available, prototypes, demonstrators, and IEEE standards being established. And also, I believe a lot of you have heard about IoT, okay, by making use of Zigbee, LoRa, cellular, Wi-Fi, NB-IoT, low orbit satellite communication, like the Starlink, we can connect all these sensors to the internet, to collect the data to the cloud, to do the processing, to obtain some more actionable insights about our power grid. And also at the home level, okay, the contact sensing can be useful in the in our smart home. Okay, in the past, usually we can only measure the energy consumption at the power panel. Okay, so which is an aggregate amount of the energy consumption. Okay, but by deploying contact sensing and retrofits to the existing equipment and appliances, it is possible to determine the energy consumption of each individual appliances, which provides so much more useful data to building simulations to analyze the energy consumption of buildings. Okay, because as you know, 1/3 of the energy is consumed in buildings. So if we can measure the energy consumption accurately and devise the corresponding energy saving strategy, it can save a whole lot in energy consumption in the world. So the operation state of the home appliances can be monitored, the EV charging station can be monitored, the energy consumption, power quality, blah, 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 can be collected for automation and control. You can monitor your battery lifetime, and the data can be sent to the microgrid for operation and selecting grid connectable or island mode. So it is a cyber physical system. Okay, a power grid equated with pervasive sensing is essentially a large cyber physical system. Okay, and due to its non-invasiveness, okay, the IoT contact sensing system is easier and less disruptive to the power system. So it can be scalable to be deployed over the power grid. Okay, but I also want to point out to you guys that I want to emphasize that I'm not trying to say the IoT contact sensing will replace the traditional contact sensor. It is not going to replace the traditional contact sensor. Instead, it will complement the traditional contact sensing. Okay, for example, in the traditional SCADA system, we already have the CT, PT. Okay, so I'm not trying to say that we need to replace them. Okay, what I'm saying that we can complement to them to complete the measurement, so as to build a pervasive sensing infrastructure to make the grid a cyber physical grid. Okay, where in the cyber world we have the pervasive sensing to obtain the sensing data, and in the physical world we do the control, protection, and microgrid operation. Okay. So, although today we just mainly talk about the magnetic sensor, I would like to also point out that we are also deploying accelerometers, acoustic sensors, optical sensors, and as well as the electromagnetic sensor that we talk about today to do the sensor fusion. Okay, remember, no one single sensor can solve all the problems. Okay, ultimately you want to have many different kinds of sensors working together so that you can do the sensor fusion and then do the data analytics, and so that you can train the model to do the force detection and also various energy management strategy and do the control. So finally, the conclusion. So I hope today I talk about the contactless sensing and magnetic sensing, and you appreciate its importance. And I hope that this today you learn something new about the contribution of contactless and magnetic field sensing in transmission and distribution, renewable energy, and wireless power transfer. So so the contact sensing can complement the traditional contact sensing to help to realize the cyber-enabled grid. And the workflow of condition monitoring start with sensors, and the contact sensing involve sensor fusion, machine learning, and data analytics. Okay, and you can provide actionable insights for predictive maintenance, anomaly detection, fault classifications. Okay, and we actively look forward to research collaboration with other colleagues, proposal, writing papers, projects, and summer program, etc. And with that, I would like to conclude my talk. So thank you for your attention. And here is my contact. Okay, this is my webpage, my email, and you can contact me to discuss further by email, by WeChat, sorry, WhatsApp, follow on Facebook, Twitter, etc., and on LinkedIn. Okay, and thank you very much. And remember, I work on sensors, smart grid, and smart city. And I welcome your questions. Thank you.
So thank you, Philip, for this very nice and informative talk. It's time for questions. If you have questions, please, yeah, thank you. Raise your hand and you can ask your question. So if no question, I have a question, Philip.
Yeah, go ahead.
It's about in slide 35, you talk about on-site validation for HVDC. Are you planning to do it? It's 35, slide 35.
35?
Maybe, yeah, the previous, not this one. This one, yeah, this 33. Yes. 33, not this one, the next one. Yeah, this, so 34 then, sorry. Yeah, this one, for voltage measurements for HVDC. Are you planning to do some on-site validation of?
Yeah, I'm looking forward to it. But right now it's difficult because first of all, there are not many HVDC overhead lines. And even in China, there are more HVDC lines, but in the United States, it's still a new thing. So yes, the answer is yes, we plan to do that. But right now, we're still looking for research partner. And therefore, that's why I mentioned towards the end, I'm looking for research collaboration. Yeah. So this is something that I want to do in the future.
Okay, thank you. And I have a question about the sensing for eccentricity. Or faults in a PM machine. Have you done it for induction machines as well, or only for PM?
Not yet. Yeah, we haven't done it in induction machine yet. We mainly done it on the PMSG.
Okay.
Yeah, but in the future we will try that.
Okay. Okay. And about the PM machines. So you talk about different faults to detect eccentricity and interturn short circuit. Is there a relation between, for example, the number of poles and the number of sensors to be installed and their location?
Yes. For example, the pattern that you see here has something to do with the number of poles that you have. Okay. And then so question, the answer one is the number of poles will affect the pattern that you measure. So in a way, it is the measurement result, the analysis has to be dependent on the number of poles. And in terms of number of sensors, so in general, more sensors the better. Okay, for example, here, for example, to determine the location. Okay, so obviously, if you have more sensors, then the interval of the sensor is closer, then you can determine the location more accurately. Okay, but then you involve more cores. Okay, and also you need to have a better multiplexer that collect the data from all the sensors. So in general, yes, more sensors the better. But on the other hand, we need to consider about the cost and the space issue.
Okay, so we have one question from the discussions. If you go for arc sensing in PV systems, how far the sensors can be placed from the arc source?
Or how far away? Is that correct? Is that what the question is? How far away the sensor can be put?
How far the sensors can be placed from the arc source?
Okay. This is a good question. Okay. Now, as let me see. here, okay, so as far as I remember, okay, so let me see, where do we put the sensor? Fault detection.
So this is a question from our colleague George Rabanal Arabah.
Yes. Okay. I need to remind myself because I have to admit that it is done by my PhD student.
Okay.
So my student know much better than me. Yeah. So as far as I remember, okay. So here is where we do the so basically, okay, here is the adjustable gap. Okay, so we have a motor that try to slowly pull apart the cable to generate the arc fault. Okay, and then you see there's a cable here. The current go the current go here and then go here. Okay, so and then we put the sensor here. So essentially, we don't need to have the sensor right next to where the fault happened. Okay, so we just need to measure the current that is involved in the arcing event. Okay, so in a way, the distance doesn't matter. It is the matter of measuring the current that is involved in the arcing event.
Okay. We have another question from Dr. Adel Razek. What about the uncertainty studies of different proposed sensors?
Okay. So I guess by uncertainty, he means the error of the proposed techniques, right? So so if my understanding is correct, okay, then so the errors, okay, there can be various of errors. Now, one error is the position of the sensor. Okay, as mentioned that here, as mentioned here, as we work in magnetism, we know that the magnetic field drops quickly due to the inverse square law. So that means the distance matter a lot. So the position of the sensor is important. Okay, so sometimes we receive the criticism saying that, hey, how do you know the precise position of the sensors? And it is true. The position matters a lot. Now, sometimes the sensor position does not matter too much. For example, we mentioned earlier on about the overhead cable measurement. Now, because we have a series of sensors here, and we can work reversely to find the cable position as well as the current, then it doesn't really matter because the algorithm will find the position as well as the current. But in some situation, if we assume that we know the position of the sensors precisely, it can be a problem because, as we know, the position, you never get the true accurate position of the sensor because of the mounting, because of the size variation of your mounting, or it's because of due to the installation process. You may have a tenth of millimeter deviation, and that can introduce error into the techniques. So it is true that there can be uncertainty, and we are still working on it to try to make it free of calibration.
Okay, so this is the question from our colleague How Song. Sorry, I can't read the entire name. I'm sorry about that. So in your slides, I see it mentioned high voltage transmission line, voltage sensing by coupling capacitor. Will this coupling measure being affected by air humidity or particles inside the air to worsen its accuracy? Also, in DC transmission line, how it avoids the magnetic field from the earth creating bias?
Okay, thank you for the question. So answer question one about the interference by air humidity or particles. Yes, this can affect the measurement. Okay, because essentially, okay, this matrix is describing the relationship of the coupling between the overhead lines and the induction bar. And the capacity coupling is due to the electric field lines between the overhead lines and the induction bar. And as below, how the electric field lines go, how does it propagate, depends on the medium. Okay, so depending on the air, it is true. Okay, that is true. The humidity and the or other particles in the air, as long as it affects the permittivity, for example, of the medium, it can affect the determination of the voltage. Okay, but of course, one way that you can deal with is, okay, you can have a humidity sensor, and then you can adjust accordingly. Okay, but I haven't done how much the humidity would affect the electric field. Okay, I know that it may affect the electric field, but I don't know how much it will affect. Okay, so I cannot answer how much uncertainty it will bring. Okay, but anything that can affect the electric field can affect the measurement. Okay, but you can rectify that problem by having the data of the humidity, for example. And then for the second question, in DC transmission lines, how it avoids the magnetic field from the Earth, creating a bias. Okay, so we haven't done that yet, but my feeling is we can have the okay. So let me see. So the DC we can because the Earth magnetic field is a DC field, and it is usually stationary. So we can measure the background field first, and then we can eliminate the bias. Okay, so it is true. The Earth magnetic field can create problem in the DC situation. Okay, but there, I believe we can try to measure the magnetic field first, and then take that into consideration. Okay, so that means we need to do a little bit of calibration beforehand.
Okay.
Yeah.
So Philip, thank you for the presentation and answering the questions. And we have to close the meeting now. And if you have still other questions, please contact directly Dr. Pong by email, as he has given all the contact details.
And here is my email, my webpage, and my WhatsApp and Twitter, Facebook, LinkedIn.
So, and thank you for the attendees. So it is for in most parts of the world the summer holidays. So thank you for attending this meeting, and hope we will see you for the next meetings, and they will be publicized at the Magnetic Society media, of course. So thank you, Philip.
Good day, everyone. Bye bye.
And bye bye.
Thank you, Philip and Yashin. I enjoyed it very much. Thank you.
Thank you. Bye.
Thank you.
Thank you. Bye bye.
Thank you. Bye bye. Thanks a lot, Yasin.
Yeah.
Thank you. Have a good day.
You too. Bye.
Enjoy the summer. Bye bye.